Evet arkadaşlar, sınav nasıl geçti? Yani çıkışta ben öyle çok inanılmaz beğendiğinize dair bir feedback almadım açıkçası. Yani teşekkür edenler oldu ama daha çok sarkastik sarkastik teşekkürler. Yani, efendim? Evet, doğru olabilir yani. Düşünülebilir. Şu anda söylemek istediğiniz bir şey var mı sınavla ilgili? Buyurun.
Mesela geçen yıllardaki çıkışlar baktığımda bir soru şey oluyor. Bu soru iki ilmi parttan oluşuyor.
Aha.
Bu sınavda ama tüm sorular hep ilk parta bağlıdır.
Hı hı.
Bunları ben çok dezavantajlı düşünüyorum. Atıyorum ilk partta bir mantık hatası, sayısal hata yaptığımızda direkt gidiyor.
Anladım. Anladım, okey. Buyurun.
Aslında şunu da deniyorum. Bir soruyu yarım saat uğraştıktan sonra mesela bir şey yanlış yaptığını fark ettim. Yani o yarım saat artık bitmişti. Şurada şey yazmak zorunda kaldım. Ben ilk farklı şurada bir ihtimal bir hata yaptım ve çıkaramadım bu yüzden diye birkaç yerde yazmak zorunda kaldım.
Anladım.
Ve bazı hızlı sonuçlarda hani açıkçası herhalde ben yanlış yaptım ya falan dedim, bilmiyorum.
Anladım. Şeyde bir problem oldu galiba. Less than or equal to şeyiyle çok karşılaştım ben. Arkadaşlar less than or equal to yani küçük veya eşit, bu ikisinden bir tanesini seçeceksiniz diye bir, yani less than or equal to bir phrase yani artık İngilizce'de. Yani ya eşit olacak ya küçük olacak diye bir şey değil. Küçük eşittir inequality'si sağlanıyor mu, sağlanmıyor mu diye sormaya çalışıyordu aslında. Bunu soranlara açıklamaya çalıştım ama orada bir problem oldu herhalde. Başka yorum olan buyurun.
İlk soruda hani ben mi yanlış düşünüyorum da şey yaptım ben. İlk sorunun C partında final value kullanmaya çalıştım. Lakin final value kullanmak için atıyorum omega r Hurwitz bir polinom olması lazım. Karşısı polinomu. Bu garanti ediliyor mu mesela kullanmak için? Aslında şu. Mesela ben bu terimi kullanıyorum orada. Ama bu terim hold edecek mi yani? Array, LA, bu değerleri sağlayacak mı? Bunu hani bir merak kullanmak.
Anladım, okey.
Yanlış değil mi?
Yani şeyi bilmiyorum açıkçası, çözümü tam olarak bilmiyorum. Orada şey oluyor olabilir. Yani biliyorsunuz final value teorem için sadece Hurwitz olması değil, aynı zamanda sıfırda olması da bir acceptable bir sonuç oluyordu. Dolayısıyla orada input şey olduğu için, sistemin polları sol taraftaysa kendisi de input'ta unit step olduğu için geçerli oluyor olabilir diye düşünüyorum ama kesin cevabı bilmiyorum. Başka yorumu olan arkadaşlar buyurun.
Hocam işlem yoğunluğu bence biraz fazla.
Zaman nasıldı? Verilen zaman kısa mıydı?
Ona değinecektim ben de tam. Kaldı yerler yetiştiremedim.
Anladım. Okey. Başka? Şimdi temel olarak şey üzerinde durdunuz diye düşünüyorum. Bir kere sorularda ilk kısımlarda hata yapılırsa geri kalan kısımlar çok götürüyordu gibi bir şey söylediniz. Buradan aldığım mesaj. Zaman kısa dendi. Sizinkisi bayağı spesifik, çok o konuda bir ders alamadım yani. 10 üzerinden kaç veriyorsunuz sınava? Hep biz mi not vereceğiz? Ya benim için önemli olan şey derste öğrenmediğiniz ama sınavda karşınıza çıkan bir şey oldu mu? Benim için section hocası olarak benim için önemli olan şeylerden bir tanesi bu. Yani bunu bu derste öğrendiğimizde bunu yapmamıza imkan yoktu gibi bir soru var mıydı mesela?
Hocam bence vardı ya. Genel olarak zordu yani.
Genel olarak zordu diyorsunuz. Mesela hangi soru şeydi? Derste öğrenilenlerle.
Ya siz bir şeyle renkli fark attınız. Yaptım herhalde ama bayağı bir kafam karıştı.
Bu derste mesela her şeyi anlatmamıza bazen imkan olmayabiliyor. Yani mesela ben burada derste mesela o messiz şeyleri birazcık ödeve koymaya çalışmıştık açıkçası. Bu ikinci soruyla ilgili de ikinci soruyu ben hazırlamıştım arkadaşlar. Yani onun suçlusu benim. O ikinci soruyla ilgili de açıkçası ödeve o birinci soruyu ben koydum. Yani ödevde ikinci ödevde bilmiyorum görmüşsünüzdür belki. Birinci soruda bir non-standart sistemin step response'un hesaplanması ile ilgili bir şeyler koydum. Bu verilen ödevlere özellikle dikkat edin. Yani sınıfta işlenmeyen şeylerin bir kısmı oraya atılmaya çalışılıyor. Sizin söylediğiniz şey de orada bir nevi. Yani derste gerçekten öyle bir şey işlemedim ben. Yani messiz bir şey işlemedim, haklısınız. Onu birazcık ödevde o mesaj verilmeye çalışıldı ama tabii olmamış olabilir, kusura bakmayın. Buyurun.
Hocam ben şu ödevlerin deadline'larını da artık yani şey bulamaz bu konuda da belki gelecek sene olabilir. Çok mantıklı değil bence deadline. Yani sınavdan mesela bir hafta sonra şu an çok da çöresim gelmiyor.
Anladım, olmayabilir, doğru. Yani şey yapmaya çalıştık açıkçası. Biz birinci ödevde biraz geciktik. O gecikmede öbür ödevin de sarkmasına sebep oldu. Yani bunu mazeret olarak söylemiyorum yani. Bir hata yapılmış olabilir. Öyle bir problem olabilir.
Tam bu konuya ek olarak şey söyleyeceğim ben de. Şimdi ikinci ödev deadline'ın 27'si yanlış hatırlamıyorsam. Ben maili gördüğümde dedim ki tamam ödeve çok verdi. Şu an sınava odaklanmam daha mantıklı.
Hı hı. Yani ödevi temel olarak bayramda yüklememin sebebi aslında şeydi, sınava hazırlık olarak bir soru teşkil etmesiydi açıkçası.
Aynen, işte grupta arkadaşlar işte ikinci ödev ödev hakkında soru falan sorunca dedim Allah Allah ikinci ödev hani sınavda çıkacak konuları içeriyor mu bir baktım öyle.
Anladım, evet. Yani şey söylemeyi de çok kendime yediremiyorum işte. Bakın sınavda çıkabilir. İkinci ödev o yüzden bakın demeyi de çok yapamıyorum yani. O yüzden bu mesajı sonraki sınavda da alırsınız.
Hocam bana şey oldu mesela, ödevle sınav yani çok fazla benzer bir şey görüyor. Ödevi çok rahat çözdüm. Çok daha böyle kısa sürede sınav için aynı şeyde olmadı.
Yani mesela ödevdeki router ayarlarken ne rakama baktım açıkçası. Ne rakamları ayarlamaya çalıştım. Çok daha zor bir router sorusu vardı aslında ödevde. Yani şeydeki sorunun daha kolay gelmesini beklerdim o yüzden ama sınavdakinin olmamış olabilir gerçekten. Bir de birazcık şey oluyor arkadaşlar. Yani hepimiz kendi aldığımız hocaların stilinden birazcık etkileniyoruz belki de. Yani bu kalabalık derslerde böyle bir şey de olabilir. Buna ne yapılabilir bilmiyorum ama böyle bir şey de var maalesef. Başka buyurun.
Hocam pardon biraz alakasız olacak.
Yok, sorun yok.
Genellikle ödev deadline'ları cumartesi geceye oluyor.
Hı. Ne zaman koyalım?
Pazar geceye olabilir diyor çünkü
Anladım.
haftalık genellikle çalışıyoruz.
Anladım. Okey, olabilir. Bundan sonrakileri koyabiliriz. Tabii ki. Okay. Anything else? Okay, thank you for your comments. I will try to disseminate this information to the other instructors of the course as well. So today we are going to try to finalize the concept of root locus. So remember, so far we have drawn root locus and there was a single parameter that we would like to be interested in, and according to that parameter we have drawn the closed loop pole locations. So, and remember, at the end of time domain analysis, we also investigated the concepts of PID controller. So today we are going to try to combine these two ideas. So we are going to try to draw root locuses with PID controllers and try to see the effects of PID controllers on the transient performance by using root locus. So today's topic is PID controller with root locus. So I'm going to consider only a single system, and into this single system we are going to combine some different types of controllers to see the performance. So let us say that we have G of S given as 1 over S plus 1 and S plus 2, and we are using this G of S in the feedback loop of a control system. I have GC of S and G of S here. That is our loop here. And we would like to investigate, especially here, I would like to concentrate on the settling time and of course steady state error. This is a type 0 system. Sınavlardan sonra ders anlatmanın yönü hiçbir zaman boş bir bakış olmuyor. Mesela sınavdan bir hafta önce type 0 sistem desem anlamayabilirler, kimse anlamayabilir derdim ama şu anda herkes performansının zirvesinde bence. So here we have the settling time, and we are going to be interested in this, and we are going to be interested in the steady state error to unit step input. Okay? So what happens with these with different types of controllers in the root locus to settling time and to steady state error to unit step input? Let us start with the P controller first, okay, and try to see what we can do with the P controller. The first thing that I'm going to choose GC of S as is therefore going to be a simple gain K. Okay? And in that case, the open loop transfer function is going to be K times G of S, which means it's going to be K times 1 over S plus 1 and S plus 2 here. Okay? Let us first concentrate on the steady state error. When I look at the steady state error, then I need to calculate what the static position error constant. This is going to be the limit of the open loop transfer function as S goes to 0. Okay? So in this case, when I let S go to 0, then I have K over 2. This means that the steady state error for this system is going to be 1 over 1 plus K over 2. That means that as I increase K, then the steady state error is going to be decreased. So then I would like to concentrate on the transient performance, and the transient performance is going to be made clearer by using the root locus. So here let us try to draw the root locus with respect to parameter K here. So here I will mark the open loop poles first. Open loop poles are at -1 and -2 here. And there is no open loop zeros in this case. So let me try to mark the points on the real axis which are included in the root locus. A point on the real axis is included in the root locus if and only if the total number of open loop poles and zeros to the right is an odd number. So this interval is not included. On the other hand, this interval is included and this one is not included. As soon as I place the real parts here, I put some arrows getting away from the open loop poles going towards the open loop zeros. And in this case, there are no open loop zeros, meaning that the root locus is always going to end when S goes to infinity. And in this case, I have to look at the asymptotes here. So when I have 2 open loop poles and 0 open loop zeros, the number of asymptotes is going to be equal to 2. And when I look at the angle of the asymptotes, the angle of the first asymptote is going to be 180 degrees divided by the number of asymptotes, which is going to be 90 degrees. And the angle between is going to be twice this number. Meaning that one of the asymptotes is going to be pointing 90 degrees, it is directly upwards, and the other one is going to be pointing downwards here. So here, let me find the intersection points of the asymptotes. Sigma 0 is going to be the summation of the open loop poles, -3, minus summation of the open loop zeros, it is 0, divided by 2, it is -3 over 2. So the asymptotes are going to be intersecting here. And then one of the asymptotes is pointing upwards, the other one is 180 degrees apart, away from it. And we have these 2 asymptotes. And in this case, it is going to be quite clear what the root locus is going to do. And these 2 poles are going to go complex, and they're going to go over the asymptotes to infinity. In this case, actually, I'm showing the closed loop poles exactly on top of the asymptotes because this is going to be the case for this specific system. When I look at the characteristic polynomial of this system, I'm going to calculate 1 over k over s plus 1 and s plus 2 here. This is going to give me the following characteristic polynomial. S squared plus 3s plus 2 plus k is equal to 0. Okay? And in this case, if I look at the closed loop poles when the system is underdamped, I will see that the real part of the closed loop poles would always be the same, and it is going to be minus 3 over 2. Okay? When this polynomial has complex roots, the real part will always be equal to minus 3 over 2. That actually means that these closed loop poles are divergent to infinity on the asymptotes actually. Okay, so in this case I can draw this specific root locus here. So in this case I can actually concentrate on the transient performance. For the transient performance I can look at the settling time, for example, of this system. So if I try to concentrate on the settling time, which is the 5%, let me say, settling time, it is 3 over d, where d is the distance of the dominant pole or poles to the imaginary axis. Okay? And in this case, I see that the settling time is going to start at k is equal to 0. What is the settling time? At k is equal to 0, what is the settling time? It is 3 seconds in this case, and as I increase k, what is the lowest settling time I can get? Lowest settling time. Yes, it is. So here, this distance, the maximum distance that I get is 3 over 2. Okay, if I divide this, if I divide 3 by 3 over 2, I see that the minimum settling time that I can get from this system is going to be equal to 2 seconds. Okay, and this settling time is going to be achieved when? At this breakaway point, this settling time is going to be achieved, and it's going to remain constant for any k value. Okay? So we see that for the proportional controller, the settling time is limited to 2 seconds, and if I want really small steady state error, then I'm going to need to increase k to large values. But if I increase k to large values, what is going to happen to the damping ratio of this system? The system is going to be underdamped for large k values. And what about the damping ratio? So if the system is underdamped, as I increase k, I see that the damping ratio is going to get smaller and smaller. Okay? That actually means that the transient response is really going to be bad. Settling time is going to remain constant, but the oscillations are going to increase as we increase k for getting small steady state error. So remember that this is why we actually introduced the PD controller, in order to be able to control the transient and the steady state performance independently. So now let us try to go into that. So when I look at the PD controller, then GC of S is going to be K plus KDS. So here, if I look at the open loop transfer function, then I see that here the open loop transfer function is K plus KDS divided by S plus 1 and S plus 2. And when I look at KP for this system, I see that it's going to remain the same. Okay? Meaning that the steady state error is still 1 over 1 plus 1 over K over 2. So we see that this KD, the new derivative term, does not really change the steady state error at all. Okay, so I'm going to concentrate on the effect of that KD for the transient response. It doesn't change anything in the steady state. So what I'm going to do in order to be able to investigate the transient performance is that I need to draw a root locus for the closed loop poles of this system. But here I have just two parameters, okay? Parameter K and parameter KD. So in order to be able to draw the root root locus, I'm going to parameterize this PD controller in a different way. Okay? So I will write here GC of S is equal to, I will take KD parentheses. Okay? And that is going to give me S plus, I have K over KD. Okay? So I'm going to get something like this. And I will call this K over KD as the parameter alpha. Okay? And when I write the resulting controller, I see that PD controller actually adds a 0 to the root locus. Okay? I see that this alpha, it is going to serve as a 0 in the open loop transfer function. So I can write here KD, and I have S plus alpha divided by S plus 1 and S plus 2. So we see that PD controller adds a 0 into the open loop transfer function, meaning that when I try to draw a root locus with respect to KD, I need to place a 0 somewhere in the complex plane, on the real axis actually. So now let us try to look at what type of things that 0 can make. So these are the planned poles. So I'm going to concentrate on the following 0 positions. So I'm going to place this 0 on the real axis, of course, but at the end we are almost always going to see that placing the 0 to the leftmost part is probably going to be the useful one. Okay? If I place the 0 somewhere here into the right half plane, do you think it's going to bring any benefit to us when we draw the root locus? In this case, when I fill in the real axis, I will get this and this. So I see that as we increase KD, when I place this 0 here, we even start to get stability issues. Okay? So now the settling time can even get smaller and smaller. Can even get bigger and bigger as this pole approaches this 0. And after some time, if we increase KD even further, then we might have even some stability issues in the closed loop system. Okay? So that is when we choose minus alpha, a positive one, we might encounter this issue. Okay? So if these quantities have different signs, then we're going to actually encounter that type of issue. So we see that this scenario is not really useful for us. So we generally do not try to place an additional 0 into the right half plane in that case. So here, what happens if we take it to somewhere here? When I take it somewhere here, then it's still going to be bad because this interval is still going to be filled with some root locus part on the real axis, and still settling time is going to be worse than before the PD controller. Okay? So what happens when we take this 0 to somewhere between those two poles? This is minus 1, minus 2, and I can put that 0 somewhere here. Okay? So then if I fill in the real axis, I see that this is the case. So do you think this is any good for us?
Better than the first case.
Yes, it is better than the first case, but is it better than the P controller in terms of settling time, do you think? In this case, we see that there is still a closed loop pole here at this location between these two. So probably we are not going to be able to get much reduction in the settling time with this 0 topology. Okay? So as I told you, usually when we place the zeros to the leftmost part of the root locus, we can get the most advantage from those in terms of the settling time, for example. Then if I place this 0 somewhere here at minus alpha. In this case, what happens? Let us try to see. I will fill in this interval, and I will fill in this interval. Arrows getting away from poles, going towards zeros. There is one asymptote, and it is pointing in that direction. So I have this. So we see that these two closed loop poles approach each other, and they're going to go to the left part of this 0, and then I will get Just this type of root locus. So in this case, why do we gain in settling time? When I increase KD to large values, we see that there are only two closed loop poles here, okay? There is no dominant poles or anything. So we see that these two poles would start moving to the left part of the root locus, and actually I'm going to be getting minimum settling time somewhere here at this break-in point. And we see that this minimum settling time is going to be indeed much smaller than the 2 seconds that we're going to get with the P controller. Okay, that we can actually make the settling time much smaller, and we see in this case here that we could even get rid of that underdamped, the minimum damping ratio problem here we encounter in the proportional controller. Okay, in this case I can even make the system overdamped and still have a good settling time. Okay, that is the PD controller. So remember that in both of these cases we could never make the steady state error exactly equal to 0. Okay, in all of these cases the steady state error was non-zero. We could make it small, but we couldn't make it exactly equal to 0. That is why sometimes for some applications we need to use integral controller. Okay? But I might have told you this before, we never use the integral controller alone. Now we are going to see why we don't use integral controller alone. So let us write I controller. In this case, our GC of S is actually going to be the following. So I have Ki over S, and the open loop transfer function is going to be Ki, and I have S plus 1, and S plus 2. Now this is my new open loop transfer function with the integral controller. And when I look at the root locus, in this case, what is the steady state error to unit step? The system type became 1, and steady state error is exactly 0. So that means that we have perfect steady state error performance in terms of unit step input. Okay? So now let us concentrate on the transient performance. So I have here my new open loop poles at -1, -2. When I fill in the real axis, I will get in this, and arrows. And how many asymptotes do we expect? 3 asymptotes in this case, and if you look at their angles, they're going to be 60 plus 120, 180, and 180 plus 120. Okay, so we are going to get asymptotes, and the intersection points of the asymptotes, I sum the pole locations, -3, minus the 0 locations, they are 0, divided by 3, the number of asymptotes. The asymptotes are going to intersect at the point -1. And then if I draw those asymptotes, they are going to be looking like this. Okay? And when I complete this root locus, then I see that these two closed loop poles will approach each other, and they're going to end up at the asymptotes like this. So what about the transient performance now? What about settling time? Do you think this is good with the integral controller only? Yes?
For the portion of Ki, it's good, but it starts showing oscillations.
Yes, for some small Ki values, I have finite settling time. But what about that finite settling time? Is it better than the proportional controller, for example? It is never going to be better than the proportional controller. The settling time is going to be always worse than the proportional controller. Furthermore, if I increase Ki too much, then I'm going to encounter stability issues here. Okay? So that is why we never actually use an integral controller alone. We always try to add those other terms, P terms, and sometimes D terms as well. So now let us look at a PI controller. when I look at the PI controller, GC of S is going to be K plus Ki over S. And when I equate the denominators here, Ks plus Ki, and I have divided by S here. And here I'm going to apply the same trick, the parameterization thing here. I will take K parentheses here. It's going to be S plus Ki over K, okay, divided by S here. Okay? So what can I say about PI controller? What is it going to add into a root locus? 1, 0 and 1 pole. And that pole is going to be at the origin, and 0 can be placed by choosing the parameters K and Ki suitably. Okay? So let me say that this is again our alpha parameter here. Okay? So we have K S plus alpha divided by S here. So what about the steady state performance? The system type still does not change because of this integrator that we are adding into the loop. That means that steady state error is still perfect to unit step input. So it is still 0, and we are going to be trying to improve transient performance by adding this new proportional term here. So here these are the open loop poles, and we are going to get also a 0 at minus alpha. So do you think this 0 is going to be useful here? If I put that 0 here, this part is going to be filled. So what is that going to be meaning to us? We have always an unstable system. So placing that 0 there is really a terrible idea. Okay? So we cannot really place that 0 here. Again, it is going to be, if I place the 0 here, for example, then this part is going to be filled, and there is always going to be a closed loop pole, which is very close to the imaginary axis. Okay? That actually means that placing the 0 here does not work either. We get still too bad settling time. Again, I'm going to try to do the same. I will place it somewhere here. Okay? So in that case, we're going to get this part filled, and this part actually included in the root locus. I'm going to draw my arrows here. And how many asymptotes do we expect in this case? We have 2 asymptotes, and they're going to be like this, 90 degrees and minus 90 degrees. The asymptotes are going to intersect at a point. The summation of the poles, sigma 0 is minus 3 minus this minus alpha position, okay? And it is minus alpha divided by 2 here, okay? So this is going to give me minus 3 plus alpha divided by 2. Okay? If I choose alpha too large, then the asymptotes will be somewhere here, and it's going to cause some stability issues again, because these poles are going to go there. But if I choose alpha, for example, if I choose alpha smaller than 3, between 2 and 3, then this 0 is going to be here, and these asymptotes will be placed somewhere here. Okay? So then that is going to fix the stability issues at least, okay? So with the PI controller, with the I controller, I had stability issues, and in this case, I could at least get rid of the stability issues. But what about the performance? What about the transient performance? It is still terrible, right? So we have these dominant closed loop poles, and they are making the settling time, unfortunately, too large compared to the P controller case. So that is PI controller, and finally I can here actually show you the PID controller performance. So in this case I'm going to write PID controller, and that is going to be GC of S is equal to K plus Ki of S times K plus Kd times S. Okay? So in this case, again, in order to be able to apply the root locus theory, I'm going to come up with a different parameterization of the same controller. So here, the first thing that I'm going to do is that I will actually equate the denominators here. It is kds squared plus ks plus ki divided by s. Okay? And in this case, what I can do here is to take this into kd parentheses, and then I can write the following. It is s squared plus k over kds plus ki over kd. Okay? And I have here s again. So now I can call these numbers as a and b, for example. Okay? And these are going to give me the following: kd, and I have s squared plus as plus b divided by s. Okay? So then what can I say about PID controller? What does it add into the root locus? 2 zeros and 1 pole at the origin. So again, now I have the flexibility of placing those zeros anywhere I like, as long as I choose these parameters correctly. I can choose real closed loop poles or real zeros, additional zeros, or imaginary zeros. Here, let us try to see what the real zero case would look like. So these are the -1 and -2 are the planned open loop poles, and I have this pole coming from the controller in order to fix the steady state performance here. And finally, I will place the zeros. Again, you have flexibility here, but what is going to work best probably is going to be to place these zeros somewhere here, let us say. Okay? So I have chosen real pole zeros here, but you could have chosen also complex zeros as well. It really doesn't matter. So here I will fill in the real part first. I have this. And I'm filling in this part as well. So we see that these are going here, and I can put my arrows again and towards the zeros like this. How many asymptotes? One asymptote only, and that asymptote is going to be pointing in negative real infinity. Okay, and we see that one of the closed loop poles is going to go there actually. So what's going to happen here? So these are going to fly left. Okay? As we increase this parameter kd here, then these are going to fly to the leftmost part. Okay? And for large kd values, which closed loop pole is going to determine the settling time? The one here. Okay? For large kd values, these ones will be the dominant closed loop poles. And this is going to determine the settling time of the closed loop system. And we see that in this case, the settling time actually for large kd values is definitely going to be smaller than 3/2. Okay? Because this pole is going to be somewhere here, and we see that this distance is going to be larger than 2 here. Okay? So for large kd values, we are even going to go below 1.5 here in the settling time case, and the steady state performance would also be nice. What about complex pole? If I place these zeros into complex domain, there is not much nothing fancy there, so I can place these zeros here and here, and what is going to happen in this case is that these are going to be filled here like this. So these are going to go like this, and I will have these two are going to fly into these zeros. All right? Minus 2 here. So by using the PID controller, we could make both the steady state error performance and transient performance much better. So here I would like to show you one interesting thing. So suppose that I would like to control the following system: S minus 1, S plus 1. Okay? I have an unstable open loop pole. Okay? I would like to control this system. Okay? I have an unstable open loop pole, and here this is my system. Okay? This is G of S, let me say. This is G of S. Suppose that I would like to control this system using the PD controller. Okay? And I'm going to choose the following PD controller. GC of S is equal to, let me say, S minus 1. What am I doing here? I'm trying to cancel the unstable pole, unstable open loop pole. Okay? If this cancellation works, then everything is good, very good. But if this cancellation does not work, I will try to see what happens in the root locus. If the cancellation works, what is going to happen is this. If the cancellation works, so let me say that there is also a parameter, controller parameter K here. Okay? If this cancellation works, then the only open loop pole is going to be at minus 1. Okay? And if I try to draw the root locus, I will fill in this part, and I will get this root locus with respect to K. This is the case when that cancellation works. But in general, when you have a physical system, you don't know its parameters. Okay? So you are not sure about this minus 1, whether it's minus 1.1, or you don't know if it is minus 1.01 or minus 0.99, etc. In general, you don't know that parameter. Okay? What is that going to turn the root locus into? So when I try to draw the root locus in that case, so here my plant pole's here, and the other one is here. And controller is going to bring me a 0, and if you can cancel it, this is the root locus. But when you cannot cancel it, that 0 is going to be, let us say, very close to this one. Okay? But not exactly on top of it. You cannot cancel it because you don't know the actual unstable pole location. Okay? That 0, let us say that it is somewhere here. Now when I fill in this root locus, okay, I'm going to unfortunately fill in this interval. It is going to be included in the root locus. Okay? And then this part is not included, and this part is going to be included. Okay? So I will have here. Now what can you say about the closed loop system? It is always unstable, unfortunately. There always exists a closed loop pole in the right half plane. Okay? So you can never cancel an unstable pole of the open loop system using a controller. If you cannot do it perfectly, and in practice you won't be able to do it perfectly, and if you cannot do it perfectly, then your closed loop system would always be remaining unstable, and that is going to cause problems at the end. Okay, so this cancellation issue is problematic when the system has open loop poles, unstable poles in the right half plane. So that is why we never try to cancel anything in the right half plane by using our controllers. That they are going to cause more problems than solve. So here we are finished with the root locus concept, and the remaining topics of the course. There are 3 topics, unfortunately. Nyquist plots. We are going to see the Nyquist plots, and then we are going to see the Bode plots. So control in frequency domain, and finally the state space systems. The state space systems are probably the easiest part of this course. Okay, so the last topic, state space, is going to be much easier than the other topics. But I will not be able to say the same thing about Nyquist plots or Bode plots. They're going to be quite non-intuitive, And if you miss some classes in between, what I'm doing on the board is going to look like it came from outer space. Okay, so it is not really going to be easy to catch on the topics. So that is why I really recommend you to follow the lectures related to Nyquist and body plots, so that when you study them yourselves, it is going to be much easier. If you leave those topics for self-study, it's going to be much more difficult than self-studying other topics in this course. So, for example, when I teach this course, I can actually teach you all other topics in the course without even looking at my notes before coming to the lecture. I can teach root locus any time without looking any notes. But I'm sure that starting from next week, I will have to study really a lot before coming to the lecture, because I have to remember and I have to find a way to make those non-intuitive concepts much more intuitive than you would find anywhere else. That's all for today. Thank you very much. Peki. Tabii şey yaparız. Onları sayarız. Neyi? Tabii ki sayılır. O gün raporunuz varsa hiç problemimiz yok bizim. Tamam.